Hi everybody, welcome back. In this video, we're going to do a simplified introduction to RAID. So this is going to be strictly at an overview level, so I'm not going to get into the actual implementation of RAID. We're not going to be looking at MD-admin on Linux systems. We're not going to be looking at ZFS or BTRFS or hardware controllers or anything like that. Basically, what we're going to be doing is talking about the different forms that exist in terms of RAID in modern operating systems. We're going to talk about the use cases and the benefits for some of them, and just kind of generally go over how they work and what they're doing. So I thought this would be a good introduction for people, being that for folks that are newer to systems administration stuff, even for folks who've been doing this for a while, storage is one of those areas of focus that is oftentimes a little bit of an obscure kind of specialty. So, sometimes people will be, really competent across the board, but then when it gets to storage, they don't necessarily know as much. So I think it's a good thing to be aware of. And honestly, when it comes down to it, for most things, if you lose the data, doesn't matter what else happens. So protecting the data is a really big piece of this. So I'm going to go jump over to my main display. And what I'm going to do just right off the bat is kind of point to the Wikipedia entry on RAID. It goes over all the standard RAID levels. It talks about RAID 0 and RAID 1 and RAID 2 and all the way up through RAID 6, and gives a pretty good overview of how they work. So one of the first things that I would recommend that you do if you are new to this and you haven't played around with RAID and you're not super familiar with this already, is to just go take a look at the Wikipedia entry and get some basic familiarity to what the different types of RAID that you can implement are. So I'm going to go ahead and pull this back over here, and then I'm going to go jump over to a diagramming application real quick. And we'll just kind of go through the different types of RAID that exist. So again, this is not designed to be super comprehensive, but this is going to be a kind of a general overview of the different kind of RAIDs that we have available. So RAID 0 equals no RAID. Right. So RAID, in terms of the acronym, is a redundant array of inexpensive disks. So there's no redundancy in RAID 0. RAID 0 is striping. So the idea here is that this doesn't provide RAID in and of itself. That said, it can be very useful in terms of performance. Basically, what we're going to go ahead and do is we're going to go take our data, which is going to normally be on one drive, and we're going to go add a second disk, right? And then what we're going to go do is we're going to stripe the data across those two drives. And this is a really, really useful thing because what we're going to go do is we're going to double not only the amount of space that we have, but we also double the amount of I/O that we have available. So in terms of the number of operations per second that we can do. And if you look at sort of a really basic graph, right, where we have the amount of time it takes to do something, we have the number of disks on the other axis, right? If we have one drive that we're reading and writing everything to, right, that's going to go ahead and be the maximum amount of time that it takes to go do our operations, because we only have one disk that's serving those operations. If we can go ahead and divide those operations equally across two drives, so if we go from one disk to two disks, one of the great things about this is we will go cut the amount of time that it takes to go do something in half. And the reason why this is a useful thing to be aware of is anytime you're doing something like this where you're looking at concurrency, we're looking at sort of a diminishing returns scenario, right? So if we go from 2 disks to 3 disks to 4 disks, right, we're going to go divide that in half again. But that's not nearly as big of a jump. And actually, I probably should have made that a little bit, maybe more about there. So that's not nearly as big of a jump as it was before. If we then go in terms of 8 disks, right, we're dividing that in half again. So the idea is each time we want to go ahead and get the same kind of performance doubling, where we're going to go ahead and be able to go service reads and writes, twice as fast. We're going to need double the number of disks to go do it. So that adds up, right? So if we're looking at, a graph over here, you can see how that sort of trend line goes. So by adding a single drive and doing this with striping, there's actually a really big benefit to that. Now, what you're also doing is you're doubling the possibility of data loss. That's the downside. So that's the big issue with RAID 0, is that you're taking more risk. That said, there are ways to go ahead and combine RAID 0 with other types of RAID in order to go ahead and get protection and performance, which is a cool idea. So that's the kind of the starting place. We then have RAID 1. And RAID 1 and RAID 0 are similar in the sense that they're both working on the basis of like 2 disks. Well, I mean, with RAID 1, you could use more, I suppose. But the idea is that RAID 1 is going to be mirroring, right? So we're going to go ahead and have one disk. We'll call this A, and then we're going to go ahead and have, A prime. We're going to have a second copy of that data on the other drive. And the idea here is that on writes, there's actually typically going to be a little bit of a write penalty. So writes are going to be a little bit slower with a RAID 1. Reads, however, potentially, depending on your implementation of RAID, can be potentially faster. So it's sort of a trade-off here, where we're getting a little bit more of a write penalty because we need to go right into 2 locations. And then for our reads, we're potentially going to go ahead and get more concurrency, similar to what we're looking at up there. Right? Not perfect, not quite as good as, RAID 0 because, it's just duplicate the data. But, that's potentially a useful thing. So, RAID 2, right? No one uses this. So the idea is that this was an attempt to do sort of a type of RAID that would allow you to go ahead and use more drives. Because one of the things that's worth noting when we're talking about this stuff and why the different types of RAID exist is this sort of historical context for it. So RAID 0 and RAID 1, that the idea is right around the same time. That's sort of were really obvious. The rest of the different types of RAID kind of evolved afterwards, and they generally evolved in order, thus the numbering sequence. So RAID 2 was an attempt, and actually probably just best to look at the Wikipedia because it's something that, since we don't really use this anymore, I don't actually sort of typically remember how this works. So this is using the controller to spin the disks to the same rotation. It basically keeps them all in sync with this. It's an interesting idea. It's using something called a Hamming code, which looks sort of like so it's an error correcting code kind of thing, right? So, yeah, not a terrible idea, but it turns out the idea was, with disks themselves having some internal data correction, the complexity of doing this on top of that didn't really give you very much benefit. Instead, once we start getting into the other kinds of RAID, that's really where we started to get the actual benefits. So it's a pretty interesting idea, right? So the next one is RAID 3. So we're going to go ahead and look at RAID 3, and RAID 3 also is very rarely used. It's still around. You can still go do it, but the idea with RAID 3 is it's basically there to go solve a problem with the earlier form of RAID, and mainly with RAID 1, which is that you're effectively doubling your storage costs when you look at RAID 1. When you're mirroring, right, you're going to be having 2 copies of your data. So it's not a very cost-efficient way to go protect your stuff. It works. It's pretty nice, but it's going to be more expensive. So with RAID 3, right, we can go ahead and have 3 drives. So the idea here is that we would have basically 2 data disks, and then we'd have a parity drive. We have a dedicated disk for parity. So what we would do is we'd take some stripes, right? And let's say, for example, this particular sector, right, on this particular stripe. So maybe it's like the 6th one in, right, for that particular stripe. Right, this guy was 4, this one was 3. Our parity value would be 7, and then if we lost this disk, we could take 7 minus 4 is going to give us the value that was on that remaining drive, right? So that's the idea for that. So RAID 3 was pretty good, but it was really only giving us a little bit more space, right? So it was basically 2 data disks and a parity drive, and then that led us to RAID 4, right? So RAID 4 is basically a parity drive, and I'll flip this over so we get P here for parity, and then N number of data disks, right? So N times D. So here D is equal to 2, right? Here D is equal to however many you want. And the idea is as the number of data disks grow, if you have, let's say, N is equal to 5, right? Well, the big benefit of RAID 4 is you can go ahead and survive with 1 disk worth of failure. So we get 1 disk worth of failure here. We get 1 disk worth of failure here. We get 1 disk worth of failure here, and we're protected. So the idea is that our data disks now become variable, right? So what you want to go do is you want to go look at how much risk you are comfortable with. So the larger N is, the higher possibility of losing data, right? So if you had, 100 disks, the odds of having 2 of those drives fail at the same time compared to N equal to 5 is significantly higher, right? So you're taking more risk the higher your drives go. And RAID 4 was pretty good. This is basically what everybody was doing for a while. But there was a really big problem with it. Mainly that if we go look at, just taking, let's say we've got X number of disks, right? So we'll say we got 1, 2, 3, 4, 5, 6, 7. So let's say we get about 16 drives, right? So we've got our parity drive here, and then we do a write, and the data on this disk gets updated. Well, now we need to go ahead and recompute parity for that stripe. So then we go do another write. This disk gets updated. So now we need to go compute parity for that stripe. We go ahead and do a disk update for this drive. This disk gets updated. And as you can see here, the number of writes going to your parity drive is also equal to N, right? So where N is the number of data disks, N is also a multiplier for how many writes your parity drives get. And what that meant is that oftentimes in RAID 4, your parity drive would burn out, right? So you'd have your disk fail, which leaves you effectively at that point right back where we started with RAID 0, right? Which is not great. If the whole purpose of doing RAID is to go ahead and protect our data, well, this is a little bit scary because we're basically, at least for the amount of time that it takes to go ahead and replace and then rebuild that parity drive, we're basically back to RAID 0. So if the whole purpose of implementing this is to make sure we don't lose any data, well, that's a bit of a scary thing. So for quite a while, people were doing RAID 4 and they were just like monitoring their parity drives and trying to go replace them as quick as possible and things like that. And then basically 2 things happened at roughly the same time. And I've talked to some people that were involved in RAID really early on, and there's a bit of dispute about the history of this. But this is the version that I kind of remember happening from a user perspective. I wasn't involved in designing RAID, so I can't speak to that incredibly authoritatively. But it's also sort of what I've read up on. So I'll basically tell you the form of history as I understood it, and feel free to pinch of salt. And it may not be 100% accurate in terms of the actual history, in terms of the way that this worked. But this was my understanding, and from a functional perspective, as a day-to-day admin, it doesn't really matter. So my understanding of the history is basically we had sort of two evolutionary trees that kind of happened here. The first one basically was implemented by NetApp, and the squarish N logo is the NetApp logo. And basically what they did is they implemented a buffer in front of their RAID, right? So basically what they did is they took NVRAM, non-volatile RAM, basically RAM with a little battery on it. And they've divided up into two banks, and basically each bank was sized so they could go do a full write across all of the disks in RAID 4, right? So they'd go ahead and fill up one of those banks, right? They'd then go ahead and do their write to all of the drives, including parity, at the same time. So instead of doing these tiny little writes, they do much larger writes, and that basically meant that the parity drives wouldn't burn out anymore, right? So they patented that. That's the sort of the evolutionary track in terms of RAID that NetApp went, and then most of the rest of the industry went a bit of a different direction, right? So we'll call this, RAID 4 plus NVRAM, right, or NV. And then the other fork that people went on was to RAID 5. So my understanding of the sequence of this is this came around a little bit after NetApp implemented RAID 4 plus NVRAM. Otherwise, NetApp just would have gone with everybody else and done RAID 5. And the idea with RAID 5 is instead of having a dedicated parity drive, they distributed the parity across all of the other drives, right? So if we had, let's say, 4 disks, so we get our 4 drives, what we would do is we'd basically divide that up into an equal number of slices to however many disks we have. So in this case, we've got 4 disks. We're going to go ahead and divide that up across our stripes. And I drew this a little bit poorly so that they're not exactly the same size in my diagram. They're the same size in real life. So in fact, actually, let's just go do this. Right, we'll make it easy. We'll do this. All right, so we've got 1, 2, 3, 4. And actually, we'll just get rid of this guy over here. All right, so now we've got our 4 drives, right? And then we're going to go ahead and do 1, 2, 3, giving us 4 slices on each one of these disks. So we get disk 1, 2, 3, and 4. And then what we do is we have our parity distributed across all those drives. So we have P1, P2, P3, and P4, right? And the idea is now instead of any individual disk getting written to more often than the other ones, assuming an equal distribution of our data, which is what we want to have, we should have basically good performance, and we shouldn't have any one drive burn out more often than any other drive. And then basically both of these trees kind of came back together with RAID 6, right? So, right. So the idea is that RAID 6, and I should note this also has one parity drive worth of failure, right? So or one disk worth of failure that we can go ahead and lose. So if you lose one disk with the RAID 5, it's basically equivalent to RAID 4. Same deal over there, right? We're going to go ahead and have one disk worth of protection, right? So the biggest sort of differentiator between RAID 5 and RAID 4 and RAID 6 is that RAID 6 allows you to go ahead and have 2 drives fail. So they're going to go ahead and allow you to go ahead and have 2 drives fail within this kind of same kind of idea. And the implementation is going to be a little bit different. So if I go back over here to my Wikipedia page and we scroll down, you'll see that the RAID 5 implementation here, right, is basically the same thing as the RAID 6 implementation. The difference here is that we add a second disk, which is, basically another copy of the parity values, right? So we basically have a drive where the parity values are going to be written to as well. So the idea is that initially we have the parity sort of distributed across all of these guys. So you can see, let me grab my pen over here. In this diagram, we have DP, right? We then have BP, CP, AP. So we're distributing the parity across those guys. And then Q is basically sort of a second, parity value, right? So they're going to go ahead and stripe that across these guys as well. So then we have EP over here, right? So the idea is basically we're doing sort of a layered RAID 4 or sort of layered RAID 5 implementation. We're doing our initial RAID 5, which protects our data disk, our data disks, and then we're doing another, RAID 5 on top of that, which includes the parity values from the other drive. So that basically gives us a second level of protection, right? So the idea is that it takes basically twice as much space, all right? So it's effectively just, the same thing as we did over here. In fact, I can probably just go copy this and then move this down. All right, so we'll say that this is going to be the RAID 5 evolutionary tree over here, right? Go back to our thing, extend these guys, right? And then what we would do is we'd, extend the number of stripes over here, and it's basically the same exact thing, right? We're just going to go ahead and have P5, and then we have a second layer of RAID as well, where we go ahead and do maybe a different color. So we say, this is P is the initial parity. Let's say that this is, we'll do what they did. We'll just use Q for this, right? So Q1, Q2, and so forth and so on. All right, all the way down, right across. And now we basically can go ahead and have two drives fail, and we're basically good to go. Because NetApp went through a slightly different evolutionary tree, basically what they did is they have, effectively a RAID 4 based DP. So we have our first parity drive, and then we have our second parity drive DP over there. And it's functionally the same idea. It's multiple layers of RAID. So this parity drive is basically a horizontal stripe. And then our diagonal RAID, or dual parity is the official name of it, but a lot of people think of it as diagonal parity. This is going to be a stripe, including the checksum for that one. And in fact, fairly recently, NetApp introduced triple erasure coding, which is, basically a RAID 7. But it's more or less just a different implementation of DP. I'll call this DP in parentheses because that's officially the name of it. Basically, what they do with that one is they add another parity drive, right? And then this one is going to go ahead and have the checksum in a different diagonal. So basically, it's going to give us two RAID DP stripes. So it works really, really, really nicely. And the big benefit that comes from RAID 6 or any of the kind of latter versions is as long as you're using enough drives, it doesn't actually cost you anymore. So if we look at the sort of costs associated with, let's say we're doing RAID 4, right? So RAID 4, right? We can go ahead and have one drive fail, right? So let's say we've got 14 disks, and we want to be fairly conservative. What we might go do is go ahead and do two RAID 4 groups, right? So we would go ahead and do is we do one group of RAID 4, and we do another group of RAID 4. Each one has a parity drive. Each one has a parity drive, and these guys are 6 drives, 6 data disks each, and then we've got our parity drives. And then basically what you would do on top of that is, and this is how most people would implement it, is then you do RAID 0 on top. So we stripe on top of that, And this is going to go ahead and give us RAID 4. And now we're going to go ahead and have all 14 disks being used. They'll all be protected, and we can happily go along our way. We can then go contrast that to a RAID DP implementation. I'm going to draw the NetApp variant, but this could be equally, a RAID 6 that's derived from RAID 5. It just, it happens to be easier to draw. So if we do the same kind of thing over here, and get the same number of disks over here, and we go do 2 parity drives, and then we basically have our 12 data disks, and then we go ahead and do RAID 0 on top of that. And you wouldn't necessarily need to go do RAID 0 on top of that, but oftentimes you will. This is basically a logical volume manager on top of that is what you're doing. So the idea is that if you're looking at using 14 disks, you're probably using some kind of storage array. So there's a good chance that you can be adding more disks on top of this later on. So by doing this now, even if you're only using those 14 drives, it future-proofs it so you can add more disks to it later on. Either way, right? So if we had some kind of issue where we had a failure, right? So we had a drive fail, right? In this scenario, right, we have one of the drives fail. Either way, we're good. There's no data loss, right? But if we have another failure, and that failure happens like that, where it's within the same RAID group over here, now we have data loss, right? Whereas the RAID 6 implementation is going to give you better level of protection. And the idea is as long as you're using the same number of disks, right? As long as you're using enough disks, right? So here we're using 14. And if you can compare those 14 disks to 2 7-disk implementations of RAID 4 with the same amount of parity, right? So in terms of our parity overhead, we have 2 drives, and then we have 2 parity down there as well. So the idea is that if you're using RAID 4, that's great. If you're using RAID 5, that's great. But if you have enough disks, if you're not using just 4 or 5 drives, things like that, if you're using 14 drives, 16 drives, 32 drives, things like that, we're starting to get into these larger numbers. It's usually better off to use a RAID 6 or a RAID DP because it's going to give you a better level of protection. So that's the kind of quick and dirty introduction to RAID. It's giving you sort of an overview of sort of the kind of the ideas behind the storage. And then probably what I'll do later on is I'll do another video where we actually look at implementing maybe RAID on Linux or things like that. So we'll sort of talk about how we actually can go set this up and take advantage of it. So hopefully that's useful. Hopefully now you know a little bit more about storage than you did when we started. If you like videos like this, and hopefully you do, because at this point it's probably like 20 minutes in. Why did you watch if you didn't? If you like videos like this, click the subscribe button. Also, we're getting close to a mile marker where we're almost at 200 subscribers. And generally what I will do as a thank you, because I enjoy you guys watching these videos and I appreciate you taking the time to go do so, is I will generally do some kind of a giveaway. So I will probably be giving away another Raspberry Pi Zero. The last time I did this at 100 subscribers, I noticed that a number of people mentioned that they didn't see the original video. So if you're watching this now and you do want to go do that, and you're interested in potentially winning a Raspberry Pi Zero, click the little bell icon because apparently that makes sure that you see all of the videos that show up. I know this sounds super, bog standard YouTuber. Everybody has the same ending spiel, but apparently there actually is kind of a reason for it. And since I do want to go, kind of give that away to you guys as a thank you, I want to make sure that most of you guys see that. So up until we get to 200 subscribers, I'm going to go keep mentioning the bell icon thing in the chat. And of course, if you're not subscribed already and you just spent 20 minutes listening to me talk about RAID, good God, man, subscribe. You're obviously a nerd. You obviously care about this stuff. Yeah. So that's some of the stuff that we'll be talking about in kind of future episodes of the channel. And I hope this was helpful to you guys. That really is my goal. And sort of making people who are new to IT early on in their career get some really good sort of foundational understanding of how things work. And then, of course, we'll talk about all the good career kind of stuff that you guys can go do as well. So thank you so much for spending your time with me in this video. Have a great one. Please subscribe, like the video if you liked it, all that good stuff. And I will see you in the next one. Have a great day.